Hey everyone, welcome to the third and final section for this class where we're going to talk about light and optics. So everything that we're going to talk about in this topic is going to be playing along with this concept of electromagnetic waves and how they interact with different types of mediums. Now, I did mention before that a lot of the stuff that we talked about in the first section, in particular with the wave section, is going to be kind of carried over here and played with a little bit. So, feel free to look back to some of those equations. I will try to let you know which ones to actually look at, but for the most part, it is a continuation of that. So, first, we want to talk a little bit about light. Now, in this section, we're going to talk about what's called geometric optics, which is basically talking about I guess you could say, the geometry of how light reflects off of different surfaces, things like curved surfaces, flat surfaces. This entire concept is based strictly on the fact that light acts as a ray, which is called the ray model of light. Basically saying that you can take light as traveling in straight lines. The reason we do this is mainly because of the fact that it works, but also because our eyes tend to perceive light as moving in straight lines. However, it will it is a little bit of an approximation and not really a full description of how light actually acts. So in this section, there's going to be essentially two different things. There's going to be a source light. This is like something that's creating the light, things like a light bulb or, in many cases, the sun. Uh, and then there's going to be something that will reflect light, which is reflect or absorb or interact with the light. Uh, this is typically how we end up seeing objects, is through one of these two light sources, through something that's actually creating light versus something that's just reflecting the light. Now, I said before that light is what's called an electromagnetic wave, and that it is not like a mechanical wave, because mechanical waves, if you recall, require mediums to travel through, so that it makes it impossible for mechanical waves to travel through something like the vacuum of space, which has no medium to disrupt. Now, light, on the other hand, can travel through the vacuum of space. The way light is actually created is through disturbances of magnetic and electric fields. What kind of makes light a little bit more unique than mechanical waves is, while mechanical waves require a medium to already exist in order for it to propagate, light actually creates its medium, and that allows it to move. It creates the magnetic and electric field disruptions in order to travel, rather than disrupting the ones that are already there. So, pretty interesting. The one thing with light, if you recall, we mentioned that there are two different shapes that waves can come in. They can come in the longitudinal shape or a transverse shape. Light is technically a transverse wave, but it's a little bit more special. It's actually a double transverse wave. It has an electromagnetic and a magnetic wave. It has an electric field wave and a magnetic field wave that are acting perpendicular to each other. Hence why it's usually called an electromagnetic wave. The reason why they are perpendicular to each other, this is something that you'll learn in the E&M course. When you deal with electricity and magnetism, you'll realize that they have this type of right hand rule, perpendicular relationship to each other. So this actually comes from the fact that the magnetic field is inducing a changing electric field perpendicular to it, and the changing electric field is inducing a changing magnetic field perpendicular to it. So it kind of works like that. going back to with light and being the double transverse wave, this means it does have some unique properties that things like sound, the longitudinal waves, don't have, which we'll talk about later. Now, light is a huge spectrum. It's categorized and split up into different frequencies, which we call the electromagnetic spectrum. So you have things like the gamma ray, which is between a frequency. These are wavelengths between a wavelength of 10 to the negative 12 to 10 to the negative 14th. Then you have X-rays, ultraviolet rays, visible light. What we see is a very, very small section of the entire E&M spectrum. And then you have infrared, radar, FM, and radio waves. One thing to note, so I've always wondered this is why is X-rays strictly broken off into these parts? Realistically, just throwing this out there because I'm pretty sure I mention it in a second, but in case I forget, the reason why we have these different setups is mainly because of how a lot of times it's a characteristic of the light or it's something about how the light is actually produced. For example, X-rays. X-rays are produced by taking electrons and accelerating them towards metal plates and having them collide. So this range of X-rays is pretty much categorized by that, is all the different frequencies that we can get by taking electrons and accelerating them and hitting them into metal plates. Um, so just want to throw that out there of why is it broken up. One thing that you may see is if you see a more in-depth E&M spectrum, you'll notice that there are actually a lot of overlaps between the different categories, which kind of goes back to the whole idea that it's really meant more as a rough idea of split up by their characteristics or how they're created, rather than just saying, oh, there's a hard division. Once you go beyond this frequency, you're entering into the gamma ray section. It's a little bit more vague than that. Now, it was found that light is the fastest traveling thing. Nothing travels faster than light. And in a vacuum, it has a speed of 3 times 10 to the 8 meters per second. And this is the fastest speed that anything could ever really can't well that no object can actually exceed. Uh, there are ways to travel faster than light. However, there's no way to travel faster than the speed of light in a vacuum. So a lot of times you might hear questions or comments saying that of adding in that little factor of in a vacuum, because it turns out when light isn't in a vacuum, when it's interacting with particles, it will move slower. And in some of those cases, those are when we're able to get items traveling faster than light, and we get some unique properties from that. For example, we talked about the Doppler effect for sound and how the what happens when you travel faster than the wave you're producing for sound waves, and you get the sonic boom. Um, Technically, we do have a similar thing for light, because, like I said, while we may not be able to travel faster than light in a vacuum, we can slow down the speed of light by having it move through other materials and then have objects move faster than it, and we end up getting a light version of Doppler effect, which is pretty interesting. I'm pretty sure I mentioned that later on. There actually is a theory that there are objects that do travel faster than light, called tachyons. So some people tend to revise that statement that nothing can cross the border of the speed of light. That if you are traveling slower originally, you cannot go faster. And if you're faster than the speed of light, you can't slow down and get slower than it. So, as I said before, one of the big assumptions that we are going to make in this, in order to do things with the optics, is that we're going to assume that light travels in straight lines. Um, this kind of goes against a lot of the things that we know about light, in particular the fact that it is wave-like. If you remember, we mentioned things about how waves can refract and diffract around materials. Um, this assumption is basically ignoring that and causes light to actually uh, kind of curve. But as I said before, a lot of this is based off of the fact of that's how our eyes perceive light. Our eyes perceive light as moving in straight lines, and this is the reason why we end up getting optical illusions, is because light doesn't always travel in a straight line, but our eyes believe it does. All right, so we're going to talk a little bit about reflection and refraction. We're mainly going to lay down the foundation. We kind of talked a little bit about it with mechanical waves, but it becomes a lot more interesting here. So these are some properties that light has. Um, Reflection, refraction, diffraction. While it is very easy to see reflection with non-light wave objects, um, refraction and diffraction are much more visible with light. Like diffraction does occur with sound, but it's not as noticeable. So we're first going to talk about light reflecting off of a plane mirror. Again, we did talk about this before. So one thing to note is that when a light strikes a surface, remember a surface being a different medium. So if it's traveling in air, if it hits something that isn't air anymore, we call that a surface. Some of that light is going to be reflected, some will be absorbed by the medium, and then some will end up being transmitted through. So we're mainly going to talk about the reflected first, and then later on we're going to talk about the transmitted part. Now, the law of reflection states that the angle of reflection will always equal the angle of incidence. Basically, that if you have a flat plane mirror here, the light comes in and bounces off at the same angle. Now, one thing to note, and this is going to be much more important as we get further on, the angle is strictly taken from the normal line. So the angle of incidence is the angle that it's coming in at. That is taken from the normal line. And this angle here, the angle of reflection, is taken from the normal line. Well, you might think, oh, well, why not just do it to here? Um, a lot of that is caused more for when the surface is non-flat, so it's irregularly shaped or maybe even curved. It becomes a lot easier to just do a normal line and then measure the angle from there. Um, it's also important that we do it here because of the fact that when we get to Snell's law, that taking angles from this surface will end up giving us wrong answers. Um, However, be very careful to the wording of the question because there are going to be times where they may give you this angle. But they will never call it the angle of incidence. The angle of incidence is strictly to the normal. They might say, oh, the angle from the ray to the surface is 30 degrees, and they may want to know what the angle of reflection is. So you wouldn't say, oh, well, if this is 30, that's 30. Well, would have to figure out what the incidence angle is and then use that to find the reflected angle. Now, that this is a lot of times called specular reflection, where you're having the light bounce off of a very smooth surface. This is the one we're mainly going to be focusing on because there's no point in talking about any other type. This is how we get images. However, reflection occurs on any surface. If the surface is irregularly shaped, like here, um, you get what's called diffuse reflection because the light will bounce off in all these different directions. With diffuse reflection, you don't actually see an image. You may see colors and such. You might see something from a reflection, but you won't get a crisp image. Like mirrors are caused by having completely flat and smooth surfaces. The more uh, rugged and rigid and bumpier the surface is, the harder and blurrier the image is going to be. This is why a lot of times you actually can see shadows off of things, like that were reflected off of things, um, off of like non smooth surfaces, but you won't see like colors and images and stuff unless it gets close to the smooth, being fairly smooth. So here we have two flat mirrors. Um, Work on this yourself. One thing I do recommend is try to draw out the picture as best as you can. It might be a little bit tough, and pay attention to the wording. All right. So you can pause the video, work on this yourself, and we'll go over in a second. All right. So the first thing to note, like I said, we have two flat mirrors that are perpendicular. So we're gonna have an L shape. It says that the incoming beam is going to make an angle of 15 degrees to the first mirror. So this is not the incidence angle. This is the angle to the mirror. And then this one, they want the angle to the second mirror. So again, we're actually going to be taking the angles from the mirror. So our diagram should look something like this. The light comes in, bounces off, hits into the other mirror, and then bounces off. So this angle is going to be 15. From here, because the normal line is 90 degrees, we know that this is going to be 90 minus 15, which is going to make it 75. Um, if this is 75, then this is 75. We could also say that this is 15, and because this is a triangle, this would have to be 75, and because this is right angle, this is 15, 15, 75. So basically, you're just using your geometry to figure out that this angle, the one that we're actually looking for, is going to be 75 degrees. Some of you may have guessed that that might have been it, but you do want to make sure that you're paying attention because there are questions in the book where instead of it being at 90 degrees, it ends up being at some other angle like 60 degrees, or it might be interacting with a triangular surface. Um, One of the interesting things is because of this, the incoming ray and the outgoing ray are actually going to be perpendicular to each other. Or sorry, not perpendicular, parallel to each other. Um, so it's going to end up reflecting back where it comes from. And this is actually kind of how the reflectors on bikes uh, are made, is by using this principle so that when light hits the surface, it kind of bounces back the same way so that you can actually see it. Interesting stuff. I think the one of the homework questions actually has something with a mirror kind of like this, and if you do have the chance to take two mirrors and put them 90 degrees to each other and look through it, I do recommend it. You'll be able to see your actual face. All right. So now, when you're looking at objects in a mirror, a lot of times it doesn't. When you're looking at the object in the mirror, while we know that the object exists outside of the mirror and it may exist to the right of us, um, for if you didn't know that, you would think, and your brain actually sees it as being inside the mirror. So again, you kind of have to think about this because every time I bring this up, people always think, well, of course it's not in the mirror. And they're using logic to explain this. But again, this is coming from what your brain is seeing. Your brain is able to decipher it from experience that it's not in the mirror because, we're intelligent beings. But um, the way our eyes see it is that it looks as if it's in the mirror, as if that's a window. So, for example, if you're looking in a mirror and you have a bottle of shampoo here, uh, the images from the top and the bottom of the shampoo are going to reflect off the surface and strike in your eye. And if you remember, light, as far as our eyes are concerned, we assume that light travels in straight lines. So when we get this light, we think and believe it as coming from inside of the mirror. So that's where those images come from. Now, if you don't believe that, uh, I would recommend pulling up YouTube and looking up videos of animals looking in mirrors. A lot of times you'll notice that animals, if they encounter a mirror for the first time, don't look at it and say, "Oh, that's me," or "Oh, those are my surroundings. This is just reflecting everything." No, they normally think of it as a window to another area. I think there's a one famous video where they take mirrors and place them inside of like randomly in the wild, and you see these animals interact and try to attack the images because they look at it and say, "Oh, there's something over there." They see it as a portal or a window rather than just a reflection. Um, so for a plane mirror, the image distance and the object distance are equal. Uh, Again, kind of makes our lives easy. Don't have to really do anything. Um, we end up calling this a virtual image. So when an image is created, um, that's inside of the mirror, we call it a virtual image, as opposed to something that could be created, which is called a real image. Now, the main difference between that is that with a real image, if you do this and you have the object, the light reflected off the object, it will actually produce a image that could be put onto a piece of paper. So, for example, here we'll just say that you could take the image formed by this shampoo bottle, and if you can place a piece of paper here where this person's eye is, and there's an image actually formed onto that, then that would be called a real image. So a lot of times the best way to think about real images versus virtual image, because it does kind of come up later on, is that if the image is produced in the real world, which is over here on this side of the mirror, it's a real image. If the image is formed on this side in the mirror world, we call it a virtual image. All right, so just a quick little geometry thing with the plane mirror. So we have a woman who's 1.6 meters tall, standing in front of a plane mirror, and we want to figure out um, how uh, how long should this mirror be, and how high above the floor should it be, so that she could see her entire body. All right, so you could pause the video, work on this self, and we'll go over it in a second. All right, so all this has to do is playing around with geometry. So first thing to realize is that if you remember, the incoming ray and the reflected ray, the incident angle and the reflected angle are always equal. Now, because they're equal, due to the law of angles and the trig functions, sine theta and cosine theta and tangent theta, SOHCAHTOA, we know that the horizontal distance that this, or maybe I should call it the vertical distance that G travels down at, is equal to the vertical distance that E travels down at, since the angles are the same and they're both the same distance apart between our eyes and the mirror. So what this means is that the top of the mirror at minimum would have to be halfway between the top of her head and her eyes. Likewise, a similar thing could be said about her feet to her eyes. The angle, the incident angle is the same. The vertical distance up is equal to the vertical distance up on the other side. So the bottom of the mirror has to be directly in the middle between the foot and her eye, since they're the same distance apart. So this mirror would have to be at minimum half her height. So if she's 1.6 meters tall, it would have to be half of that. And then the height above the floor would have to be the distance between her eye, half the distance between her eyes and her foot. So half of 1.5. So here we have, it says here that the full length mirror only needs to be half of her height, and it needs to be placed 0.75 meters above the floor. So it's pretty interesting. And if you notice, it has nothing to do with the distance that she is from the mirror. So what this means is that um, the no matter how far or how close she gets, as long as you know the light has enough space to actually reach the mirror, you will technically see your entire body. This is also very important if you end up living in a house with someone who is of a different height. Like you've probably seen a lot of pictures on social media of people posting where one person in the house hangs a mirror, and then their significant other is either super short or super tall and can't see themselves. Basically, if you want to get an idea of how big the mirror should be, the top of the mirror should be between the top of the head and the eyes of the tallest person, and the bottom of the mirror should be between the eyes and the feet of the smallest person. So if you do that, uh, everyone would be able to see their entire body at all times. Now, like I said, the plane mirrors are boring. That's the most that we're going to get into with them. What's more interesting is curved mirrors. Now, there are two shapes that curved mirrors can come in. There are convex mirrors and concave mirrors. Now, right off the bat, I'm going to tell you that after I mention which one's which, I'm probably not going to call them convex and concave. You'll see problems in here that talk about them. You'll see problems in textbooks that talk about them as being convex and concave, but you're going to see me call them in particular converging and diverging instead. And you'll see why in a second. And when we get to the lenses, it will make a lot more sense why I call them converging and diverging rather convex and concave. Um, so here, concave mirrors tend to be made for cosmetic and shaving things because a lot of times, at least from the distance that we use them, they'll make images look much larger. So they kind of act as a magnifying mirror. Uh, but a lot of times we end up using convex mirrors as either rear view or security mirrors because what they'll do is they'll condense a large area, a large image into a smaller section. So ideally, it has, I guess you could say, more information in it. Though both of these will end up distorting the image. So this is what a convex mirror looks like, and this is what a concave mirror looks like. So concaves are nice. What you'll see here is that the lines, when they bounce off the mirror, will actually come towards each other because of this curved shape, while the convex mirror will actually cause them to bounce away. So again, this is what I call the converging mirror, and this is what I call the convex mirror. Now, a quick little side story. This ended up actually biting me in the butt a while ago. So I had to take a test to basically prove how well I knew physics. And despite my wife's recommendation that I should study stuff, I decided against it. And they didn't give us any reference tables, which was fine. I knew all the equations in my mind. But they started bringing up convex and concave mirrors, and they didn't have any diagrams with it. So actually, it wasn't convex and concave mirrors, it was convex and concave lenses. And this ended up screwing me up because the numbers change depending on which one it is. And because I only knew them as converging and diverging, I wasn't sure which one was which. So I kind of had to go through this whole like 10 minutes to try to figure out which one was which. And it ended up wasting a lot of time. So thankfully, I was able to actually figure out which one was which. Like I said, you'll see why later on. All right. Now, one thing that's very interesting about rays, so if we assume or if we consider a case where parallel lines are coming towards a mirror, um, then every single line is going to abide by the whole um, law of reflection, that as they come in, they're going to bounce off at equal angles. But because of the way uh, that the mirror is curved, they're all striking the surface at different angles. So the angles, while always the same to the normal line, are actually going to be bounced off at different ways. And it turns out that they end up coming towards a single point. Uh, Now, that point is what we actually call the focus point. Um, and yeah, so it does say that it doesn't do it completely. The more curved it is, usually it's a lot more noticeable for smaller curved mirrors. But yeah, we end up calling this the focal point, the point where all the parallel lines will end up crossing towards. And we're going to take this to, so there's a few terms here, like there's this term principal axis. So the principal axis is pretty much the line that goes towards the center of the mirror in a along the radial length, if you will. So if these lines are all coming towards parallel to this principal axis, they're going to land along the principal axis on the point called the focal length or the focal point. Um, and then if they didn't come at an angle, because some people have asked me, what if the angle is coming this way? So it's on an angle from the principal axis. It actually still abides by the law of reflection, and the focal point will actually then be an equal angle uh, below the principal axis. So interesting enough. So it turns out that the focal point is half the radius away. So a lot of times you're going to see diagrams of curved mirrors and lenses, and you'll see these 2 points noted, a C for the center of curvature and F for the focal point. So this is pretty much what we're going to end up assuming. This black line here is our principal axis. The focal distance goes from A to F, and the center of curvature goes from A to C, which is double that original distance. All right. Um, so another thing about the focal point, and this does play a part later on, is that it's the point an image is formed when an object is infinitely far away. So for example, because of the fact that all the light rays end up crossing at that section, that's why we call it the image point. Because one thing that you're going to see as we do these geometric optics with these mirrors is that wherever the lines cross is where the image is formed. So you may see that, and that will play a part later on, or in some cases. Now, as I said before, spherical mirrors don't actually pinpoint it an exact focal point. There are some little defects, and it'll get close to it. The defect is called the spherical aberration. Oh. So just keep that in mind. Now, if the object is not infinitely far away, we can still figure out where the image is created by using what's called a ray diagram. Now, you want to make sure that you practice drawing these ray diagrams as much as you can. I know in a lot of the questions I give you the ray diagrams almost right away, but you want to try to draw it yourself. In fact, on the test, I will ask you to draw a ray diagram, or at least sketch one. These are really good because first, if you do use a ruler and you're being very precise, it will end up telling you where the exact image will be formed. However, you could just use it as a quick sketch to kind of get a rough idea of what it is and be able to check your answers afterwards. Now, there are only three lines that you have to draw in order to determine where the image is going to be formed. And wherever they cross, that's the image. So what you normally do is you draw, or if you're given this, like I said, you draw this curved mirror, you draw the focal point and the center of curvature, and then you draw the object wherever it is. Again, eyeball it if you're just doing a quick sketch. If it's right in between, you put it there. If it's closer to the focal point, you might want to put it a little closer. And then you're going to draw three lines. The first line is going to go parallel to the principal axis from the top of the arrow. It's always to the top of the arrow. So you do it to the top of the arrow, it goes parallel. And if you recall, one of the things I just said was that parallel lines will go through the focal point. So the line that gets reflected is going to go from the mirror through the focal point. So this is our first line, parallel to focal. The second line is basically the opposite. We take a point that's going through the focal, and that means through a similar logic that that line would have to be parallel, because again, any parallel line reflected will go through the focal. So the opposite statement also holds true. So right here, just with these two lines, I can already tell that my image, the top of the arrow, is going to be formed right here. But there is one last line that you could draw, which is the line going through the center, which is basically just a straight line. There's no reflection at all for that. Or I guess technically the reflection would just be 0 degrees, just there and back. So that would be the third line that you draw. From the top of the line to the center of curvature to the mirror and straight. And then all 3 points end up crossing here. So the top of our arrow is going to be right at this location. All right. So I'm going to quickly show how the magic equation is going to be derived, but I'm going to speed through it. All right. DO is going to be used to represent the object's distance from the mirror. DI is going to be used to represent the image's distance from the mirror. HO is the object's height. HI is the image's height. And then F is going to be used to represent the focal distance, so the length of the focal point. Turns out that there is a ratio between these. It kind of goes with the whole geometry thing. So again, because the angle that it comes in at is equal to the angle it comes out at, then we know that from SOHCAHTOA that the distances and the heights have to be proportional. From there, they just plug in, OF and that. And then you can take DO minus F to represent this distance, and then the focal length for FA. When we take this and we maneuver things around, we end up getting this equation. This is what we call the mirror equation. It is super, super important because we're going to also use this for lenses. And then another equation we could use is this, the magnification. Basically, it's the ratio of the heights, the image height over the object height, or similar thing for the image distance, the negative of the image distance over the object distance. One thing I want to note is that if is about the sign conventions. If the height is positive, so the image's height is positive, that means that the image is upright. So this image here in this diagram would actually have a negative height because it's inverted. And then DI is positive if the image is in front of the mirror. So again, here, this image is formed here, so it is a positive image. If, on the other hand, this image was formed back here, that would be a negative image, which we'll see in a second. Um, this is also going to be used to kind of refer to whether an image is real, like this one, or virtual, which would be in here. Um, okay, so here's the first question. Pause the video. As I said, um, make sure that you draw a diagram yourself. Pause the video. We'll go over in a second. All right. So here what we have is a diamond ring. It's placed 20 centimeters from a mirror that has a radius of curvature of 30. So from here I know that the focal length is 15. So this image is going to be somewhere between the um, the focal length and the radius of curvature. And they want the position image of the image and the size. So I'm just going to do a really quick diagram. There's the arrow. So there it is, halfway from there. I'm going to take my lines. So the first line is going to go parallel as best I can. And then it's going to go through the focal point. My second line, oh, no, I want to keep that purple. My second line is going to go from the top of the image through the focal point. Now, I do want to clarify that I'm using paint. So, this is just going to get a rough idea. And then the third one, I'll do this, goes, oh boy, I'll do from here to here. Now, what I can tell here, so while all three of my lines aren't necessarily crossing, a lot of this has to do, again, with my very poor drawing and spacings of things and spacing of the curves and stuff. But what we do get is this. First, all these lines are crossing past the center curvature. So my guess is that the distance, the image distance, is going to be something like 35, if I had to guess. And I know that the image is going to be inverted, so it's going to be some sort of negative number, and it's going to be a number bigger than whatever I have. So I think the original one was like 1.5, so I'm going to say it's something like 2.5. And we'll see if my number is correct. So then I end up getting an image that's formed like that. All right, so this is my approximation. Don't get upset if your image isn't, if the lines all don't cross. Typically, you just go with the first two lines a lot of times, but it is always good for that third line just as a quick check. All right. So yeah, right here, this is a more accurate drawing. So the radius of curvature is 30, which means our focal length is 15. We're going to plug it into the mirror equation, solve for di, and we get 60 centimeters. Okay, so I was off. I guess I should have paid a little bit more attention to my scale that I had, my poor scale. But it's 60, and because it's a plus, that means it's in front. So I did get that. And then magnification is going to be 3 times and negative. So the height will end up being negative 4.5. So it is. So while my guess numbers were way off, at least the signs and the location and the format were close enough. So what this means is that when I get these numbers, I can actually deem that these were accurate, that I did not make a mistake with any of my signs. All right. So here's the next question. You can pause the video, work on this yourself. Again, do the diagram yourself, and we'll go over it in a second. All right. So here what we have, the object is now going to be placed inside of the focal length. So we still have the same radius of curvature, but now when we have the object, here we go, uh, it's now going to be placed right in here. Uh, there we go. I'm going to put it here. One thing that I want to point is that the distance between these two and the distance here isn't actually half on my diagram, so could be a big reason. Now, when we make our lines, it's going to be a lot more interesting. So we're still going to do the first one of a line that goes through the focal point, except if you realize it's not going to strike if we go this way. So what we have to do is we're going to extend it out like this, like that. And then this line is going to go parallel, like that. Um, or I'm going to skip the next one, but I also know that I'm going to have a uh, center of curvature line that goes like this. And you'll notice that so far none of these lines are actually crossing. Um, so the next one I have to do is a focal line that goes that starts off parallel, and then it's going to end up having to cross through the focal point. This one actually ends up being a lot tougher. We'll try to draw this as best I can. It's not really like that, but you'll see what we're going to do in a second. The thing is, actually, it doesn't really bounce off like that either. I'll just put it anyway. But it turns out that none of these lines are really crossing the way they should. So what you end up having to do is you're going to end up having you're going to end up having to backtrack these lines. So that line gets backtracked, this line gets backtracked, and this line gets backtracked. And what this tells me is that the image I create here is going to look like this. So this time we're actually going to be creating an image on this side. So a lot of times when the lines don't converge like they're supposed to, this would be what we normally call as converging. I mean, sorry, not converging, diverging. After you draw your lines, you then have to backtrack the reflections. Not like I didn't backtrack this incident line, I backtracked the reflected line. You're going to backtrack these lines to see where they would cross. All right. So from here, I could see that it's definitely bigger than what I have. I'm actually going to say that this one is has a magnification of about 3 times the original, and it's going to be a +3. As far as distance, I'm going to guess that it's going to end up being a negative. I'm going to say -20. All right, let's see how close I am with my numbers. All right, so here we go. So this was what we ended up getting. One thing to note is you might think, oh, well, these two lines crossed. They kind of drew it better than what I did because the line that I drew that went like this was not part of the reflection. That was just me getting an idea of the angle of the line that would have come from through the focal length in order to figure out the parallel. So none of these 3 lines will cross. They all diverged. Again, that's why we have to backtrack them like that. So looks very similar to the drawing I did. Just, say so myself. So we take the equation again, we plug the numbers in, and we solve, and we get it's minus 30 centimeters behind the mirror. So let's see, what was my guess? Minus 20. So not too bad, a little bit off. We plug in the numbers into the magnification equation. We get plus 3, which spot on right there. Um, which then means that if it was originally 1 centimeter tall, it's now going to be 3 centimeters tall. So interesting enough, this image is now what we would call a virtual image, now that it's inside of the mirror, or behind the mirror, if they will. All right. So um, yeah, when you do convex mirrors, um, the same thing applies, but a lot of times you're going to end up getting images that are typically almost always virtual, upright, and smaller. With the concave mirrors, where the lines always converge, it's only like that when you're very close to the mirror. Um, so it's not always like this, but for diverging, it's always, no matter where you are along the line, the images that you're creating are going to be virtual, upright, and smaller. All right, I'll go through the diverging one later on, um, but these are just some problem solving tips that you want to kind of go through. You want to draw a ray diagram just to get an idea um, of where you're going to be, where your numbers are supposed to be. Use the mirror equations, and then just pay attention to these sign conventions. Um, all right, that's where we're going to end today. We'll continue on with our discussion tomorrow or in the next video. So if you have questions, please let me know. Otherwise, I'll see you later.